Hello guys, welcome back. This video we are going to talk about the diesel cycle. And diesel cycle is the ideal cycle for compression ignition engines. If you remember from the Otto cycle or the spark ignition engines, we had an air-fuel mixture that we compress, and because of that we increase its temperature and its pressure. And let me change the color, and we need this spark. Because we have a mixture, we have a limit on the compression ratio that we have, because temperature gets so high that it will get to the ignition of the air-fuel mixture. So that limits our compression ratio that we discuss. We have this expression, remember, that we have so the higher the compression ratio will be, our efficiency will go higher, but this ignition will limit our efficiency. So we get rid of this by compressing just air, and once that we have a higher compression ratio, that will increase the temperature. And once that we are at the top, that center, let's say that we have here our top, that center, we inject the fuel. Now, the moment the fuel enters in contact with air, will start burning, so that will make our piston to go downwards, and because of that, pressure will be held constant. So that's the main difference. If you notice, we have an isentropic compression. Before we go to this, let's this is the PV diagram for an actual cycle. You can see that we have the suction, have a pressure below the atmosphere, suction, then we have compression, and then we have the burning of the mixture, and because the piston is moving downwards, the pressure tends to be constant. Then we have the expansion, and then we expulse. We have the compression again, and then exhaust, the combustion gases. So a way to represent this as simplification will be the isentropic compression. We substitute the combustion by a constant pressure heat addition. Then we have a second isentropic process, which will be the isentropic expansion, and then we have the constant volume heat rejection, which will model the exhaust of the combustion gases. So we don't have a spark, we have the injector, and as we mentioned, we have this injection to occur when we have the piston at the top, that center. Before we go to this, let's see an animation. Here we have the four processes. We have the induction, what we call the suction, then we have the compression stroke. The power stroke is when the combustion takes place in the exhaust. Here we see it a little bit closer, and now what we're going to do is we're going to stop at each stage. This is the suction, the valves open and we admit air, then we compress it, we increase the temperature of that air, and in this injection we inject the diesel at the same time that the diesel injects start to burn, and that will create the expansion of that gas, and we have the power stroke. We're moving down. Then when we are at the top bottom that center, we open our valves, and then the piston will start moving up and exhausting. So let's repeat it again. Remember that induction is the same as suction for our description. Okay, so if you see the isentropic compression and the isentropic expansion and the heat rejection is exactly the same as the Otto cycle. The only different process is the Q-in. So we are going to analyze this. Remember that our first law for closed systems, because this is a closed system, we have a fixed mass. We're modeling this way. We have Q in minus Q out plus work in minus work out equals U3 minus U2. Remember that in this process we have a constant pressure, heat addition. So because of this, we know that we can get rid of Q out. We have Q in. We don't have any work in, but we do have work out. We have work out because we have a change in volume, right? So we can solve for Q in. Plus U3 minus U2. Now, this work out, if we evaluate our integral of P dV, we will get that pressure is constant, and then we have the difference in volumes. So we can subtract, we can rearrange, put all the threes together, so will be P V3 plus U3, and then minus PV2 plus U2. And you may recognize this or remember this from your fluid mechanics, and you remember that this is the definition of enthalpy. So at the end, Q in will be H3 minus H2, and this will be the only difference between our ranking, our Otto cycle and a diesel cycle. The second difference will be we could have a new ratio that will be V3 over V2, and this will be the cut ratio. So if we see in our expressions, you can see that we get to the same expression here. And of course, this expression is for constant specific heats. We can get also variable specific heats. This can be evaluated with table A17, which is variable. Now we introduce a cutoff ratio, and if we perform this analysis again with constant specific heats, we're gonna get, to this expression. Let me just highlight it for you. This expression we want it only for constant specific heats. The other expression will be, this will be general all the time. Now, you can see that now we can get to higher compression ratios. We can get to compression ratios up to 20, 22, and that will increase our efficiency. And we can get to these high ratios because we don't have the fuel mixture, we have only air. And this cutoff ratio, the greater the cutoff ratio, the less efficient you have. If you have a cutoff ratio of 1, in the limiting case, you are having an Otto cycle. So let's get a little bit closer attention to this. This number here is Otto, right? So since this number is always greater than 1, you're subtracting more. So the efficiency of Otto will be always higher than the efficiency of diesel for the same compression ratio. And you see the same in this graph. In the limiting case, Otto and diesel will be the same. That means that we don't have any cutoff ratio and you have an instantaneous heat addition. But as you start to increase this cutoff ratio and you separate from the Otto, your efficiency will start to go down this direction. Okay. Well, next video we are going to solve some problems on the diesel. Finally, we have a combination that we will call the dual cycle, and in this dual cycle we have some part that will be at constant volume and then some part that will be at constant pressure, and so the difference here will be again in this section, right? So the Q in will be computed as UIX minus U2, and this is the constant volume portion plus H3 minus HX, and this is the constant pressure portion. So this is the only difference. The isentropic compression, expansion, and heat addition, the heat rejection will be exactly the same. Okay, well, next video we're going to solve some problems on diesel and Otto. I guess that will be 2 or 3 different videos. Our next video also will be on Brayton cycle. Okay, thank you and take care.